Hey everyone, ready for a real mind bender? We're about to explore how chaos can lead to order, even life itself.
Yeah.
We're going deep with John Gribben's deep simplicity, and you've sent us bits from all over the book.
Yeah, we've got everything from basic physics to the Gaia hypothesis. It's going to be wild.
Our goal today, to help you grasp these big ideas, see the surprising links between them and leave you thinking, whoa, I never saw it that way before.
It's like complexity boot camp, but, without the push-ups.
Exactly. So Gribben starts us way back with the scientific revolution. Remember the whole debate about whether the Earth went around the sun? Huge shift.
It was a turning point for sure. I mean, figures like Martin Luther, they really resisted this new idea.
Yeah, going against what everyone had always believed.
But Galileo, he had that famous line, the Bible shows the way to go to heaven, not the way the heavens go. Science was already challenging those long-held beliefs, even way back then.
And that's a theme we see again and again throughout history, isn't it? Those early scientists, Galileo, Kepler, Newton, they really built the foundation for what we call classical physics.
They did, but their methods were just as important as the discoveries themselves, though.
Right, like the way they approach things.
Observation, experimentation, testing their ideas against reality. That's the scientific method in action. And look what it led to. Galileo figuring out acceleration, Kepler cracking the code of planetary orbits, Newton giving us those laws of motion and gravity.
It's incredible how each discovery kind of built on the last.
Yeah.
But they weren't afraid to use simple models to get started either, right? Like the whole thing about a world without friction.
Exactly.
That doesn't really exist, but
It's a starting point. Scientists use these idealized models, and then they add in the real-world messiness, like a rough sketch before you get into the details.
makes sense. But even with those simple models and Newton's brilliant laws, there are some things they just couldn't solve.
No.
Like the three-body problem, right? Trying to figure out how three objects orbiting each other would move.
Yeah, that one gets messy fast.
Right, like way more complicated than you'd think.
And it highlights a key point here. Even with our best theories, some systems are just inherently unpredictable over really long periods. Newtonian physics, it works great for a lot of things, but it's not a perfect crystal ball.
No predicting the future for millions of years, huh?
Nope. And then things got even more interesting with Maxwell and his work on electromagnetism.
Oh yeah, that was a game changer.
Absolutely. Those equations he came up with, they're elegant, powerful, but they point to something strange about time. They suggest that processes should be reversible, like rewinding a film.
Okay, that's weird, right? Because in our everyday life, time only moves forward.
Exactly, and that's the head-scratcher. So how do we make sense of that?
Yeah, how do you reconcile these contradictory ideas about time?
That's where entropy comes in. Think of it this way. You have a perfectly ordered deck of cards. Shuffle them, what happens?
Well, they get all mixed up, obviously.
Yeah. They become disordered, right? Entropy is a measure of that disorder. And the universe, it has this natural tendency to go from order to chaos. Entropy tends to increase over time.
So entropy is kind of like the arrow of time, always pointing toward more messiness.
That's a great way to put it, and it's a big question in physics. How do you reconcile those reversible laws that govern tiny particles with this irreversible increase in entropy in the larger world?
Yeah, it's like there's this disconnect between the micro world and the macro world. And that brings us to chaos theory, right? That idea that even simple rules can lead to totally unpredictable outcomes.
Exactly. It's not just about things being random. Chaos theory says that even systems with fixed rules, like physics, they can be incredibly sensitive to their starting conditions. Even a tiny difference at the beginning can lead to totally different results down the line.
So that's the butterfly effect. Butterfly flaps its wings in Brazil, causes a tornado in Texas.
It's a great image, right? It shows the limits of prediction, even when we understand the basic rules. So we might be able to predict the weather for the next few days.
But good luck predicting it a year from now.
Exactly. But here's where it gets even more mind-blowing. Chaos isn't just about unpredictability, it's also a source of creativity, of complexity.
Hold on, so you're telling me chaos can actually create order? That seems completely backwards.
It's not that chaos directly creates order. It's more like systems on the edge of chaos. They're primed for these complex patterns to emerge. Imagine a constantly changing landscape.
Okay, I'm picturing a landscape, but how does that connect to order?
Think of it like this. The system's always being nudged away from this perfectly balanced, unchanging state. These nudges that could be random or caused by energy flowing through, they force the system to explore new possibilities.
Like shaking up a snow globe. All that settled snow gets disturbed, it forms new patterns.
Perfect analogy. And sometimes these disturbances, they lead to spontaneous order, like snowflakes, right? Intricate patterns forming from water molecules.
So instead of everything going to chaos, it's more like this dance between order and disorder.
That's it. And this dance is especially important when we start talking about life, which is, the ultimate example of order emerging from this chaotic mix of molecules.
So we've got this universe where chaos can actually spark complexity, even something as intricate as life.
Yeah.
But how do we get from, simple patterns to, well, US?
That's where Darwin's theory of evolution by natural selection comes in. But first, it's super important to remember evolution itself is an observable fact.
Right, it's happening all the time.
We see it all around us. Darwin's theory is a model for how it happens.
It's like gravity exists whether or not we understand Newton's laws, but his laws help explain it.
Exactly. So think about Darwin's famous finches, on the Galapagos Islands.
Oh yeah, those birds.
Different finch species, they evolved these distinct beak shapes,
All different, yeah.
each one perfectly suited to the food on their specific island. So over generations, the finches with the best beaks for their environment.
They were the ones who survived.
Right. They were more likely to survive, reproduce, and pass on those traits.
So it's not like the finches were deciding to change their beaks or something.
No conscious decision there.
It was the environment kind of doing the selecting.
Exactly. The environment was selecting for the traits that help them survive and reproduce. But here's where it gets really interesting. Natural selection, it's not just about individual species changing on their own.
Right, there's a whole ecosystem.
It's about species interacting, constantly shaping the evolutionary landscape.
So it's more like a dance between all these different species.
That's a great way to put it. And we can actually use game theory to understand this. Imagine two types of birds. Hawks, who are super aggressive, always fight for food. And then doves, who are more passive, try to avoid conflict.
Okay, I can picture that.
So a hawk meets a dove, easy win for the hawk, right? Gets the food. But what happens when a hawk meets another hawk?
Oh, that's got to be a fight.
It is. And they could get hurt, even if one of them wins. Doves, they save energy by not fighting, but they might miss out on meals.
So is there even a best strategy? Sounds like it depends on what everyone else is doing.
You got it. Game theory shows us that the success of any strategy, it depends on what the rest of the population is doing. This leads to these dynamic shifts, the hawk and dove populations kind of going up and down over time, constantly adapting to each other.
So evolution isn't about reaching one perfect state of fitness. It's more like navigating this landscape that keeps changing.
You nailed it. That's a fantastic way to picture it. And in fact, scientists call this the Red Queen effect. Species are constantly evolving, not just to get ahead, but just to keep up with the other species they're interacting with. It's
Like running on a treadmill, you're working hard but staying in the same place.
Exactly. And this brings us back to that chaos idea from earlier. Remember that sand pile model?
Yeah, the one where adding just a few grains of sand can set off those huge avalanches.
Right. It showed how these complex systems can be sensitive to even tiny changes.
So even a small thing can have big consequences.
That's the point. And this same idea applies to ecosystems. Small changes, like a new species arriving, a change in climate, even a random mutation, those can trigger big shifts in the whole system.
So even something seemingly insignificant can have ripple effects through the whole web of life. Everything's connected.
It really is. And this leads to the concept of punctuated equilibrium. Long periods of stability, then suddenly, boom, a burst of change. Those bursts can be triggered by those sandpile events, like a mass extinction or the rapid rise of new species.
It's like the Earth taking a big leap forward.
That's it. So we've got evolution, game theory, chaos, and now punctuated equilibrium, all shaping life on Earth.
Okay, this is where it all starts to click. But it's not all about competition, right? Because we also see cooperation in nature.
You're right. These same principles can explain cooperation and symbiosis. Remember the Gaia hypothesis, the idea that the Earth itself is a self-regulating system.
Right, life on Earth isn't just existing in the environment, it's actually shaping it. It's pretty wild. Tell me more.
Okay, so think about our atmosphere. Lots of oxygen, super reactive stuff, but it's been pretty stable for millions of years. How is that even possible?
Yeah, good question.
The Gaia hypothesis says that life itself keeps things stable. It's this intricate dance of feedback loops, plants, bacteria, oceans, the atmosphere, all working together.
So like a giant thermostat, but for the whole planet.
Yeah.
And life is the one adjusting the temperature.
You got it. And to show this, James Lovelock, one of the guys who came up with the Gaia hypothesis, he created this computer model called Daisy World.
Daisy World. Sounds kind of cute for something so, profound.
It's simple, but it gets the point across. Imagine a planet covered in just black and white daisies. The black ones absorb more heat from the sun, the white ones reflect more.
Okay, I'm picturing it.
So if the planet gets too hot, the white daisies would thrive, reflecting more sunlight and cooling things down. And if it gets too cold, the black daisies take over, absorbing more heat. Ah, so they balance each other out.
Exactly. And that simple feedback loop, no brains involved, just daisies, it's enough to keep the planet's temperature stable, even when the sun's heat changes.
Wow, so Daisy World shows how life can impact the whole planet, even without, like, a brain or a plan.
Exactly. But what about real-world examples? Well, one cool one involves the oceans and a compound called dimethyl sulfide, or DMS. It's produced by marine algae.
Okay, tiny algae in the ocean, releasing a chemical. How does that affect the whole Earth?
Well, DMS in the atmosphere, it helps form clouds. And clouds reflect sunlight back into space, cooling the planet.
So these tiny algae are messing with the global climate. That's crazy.
It is. But it's not just cooling. DMS also moves sulfur from the oceans to the land, where it's essential for life.
So it's this hidden connection between the oceans, the atmosphere, and life on land. Amazing. But if the Earth is this self-regulating system, how do we explain things like ice ages? Those seem like pretty big disruptions. Great question. And Lovelock actually suggests that even ice ages could be part of Gaia's self-regulation. Maybe they're triggered by external factors like changes in Earth's orbit.
Okay, so something kicks it off.
But they're also influenced by feedback loops involving life.
So life might actually be making those ice ages worse.
It's a possibility. For example, during cooler periods, you have more wind-blown dust carrying iron from the continents to the oceans. And that iron acts like fertilizer, helps algae grow like crazy, and guess what? More algae, more DMS, more clouds, and the planet cools even further.
It's like a chain reaction, but instead of leading to disaster, it's part of this bigger cycle.
But it makes you wonder, with all the changes we humans are making, are we pushing things too far? Like, is there a point of no return?
That's the big question, isn't it? We've seen how resilient the Earth is, how good it is at keeping things balanced, but there are limits, like in that Daisy World model.
Yep, the sun got too hot too fast. Even those daisies couldn't keep up, and that's the worry with what we're doing. Pumping greenhouse gases into the atmosphere, changing the climate faster than a lot of species can handle. We're testing Gaia's limits, that's for sure.
It's like we're running this giant experiment, but we don't know what the results will be. Scary.
It is. The Earth's systems are complicated, and figuring out exactly how they'll react to what we're doing is really tough. But what we do know is that we're in uncharted territory, and the stakes are high. We'll explore that more in the final part of our deep dive.
All right, so we made this incredible journey from chaos to Gaia, and now it's time to talk about the big impact, us, humans. We've become this force of nature, changing the planet like no other species. But is that a good thing or a bad thing?
That's the question that keeps scientists and philosophers up at night. We've seen how life shapes Earth, how resilient these systems can be, but we also know there are limits.
Right, like in that Daisy World model. It was all about balance.
Exactly. And that's what worries a lot of people about what we're doing. All those greenhouse gases we're pumping into the atmosphere, they're changing the climate faster than some species can adapt. We're pushing Gaia's limits, that's for sure.
So are we approaching some kind of tipping point? Like a point of no return for the planet?
Hard to say for sure. Earth's systems, they're incredibly complex. Predicting exactly how they'll respond to everything we're doing, it's a huge challenge. But we definitely know we're in uncharted territory, and the stakes are high.
Yeah, and it can feel kind of overwhelming. But is it all doom and gloom? Is there anything we could do to, change course?
I wouldn't say that. Actually, understanding chaos and complexity, it can help us make better choices. Remember, small changes can have big effects, just like that butterfly flapping its wings.
Right, the butterfly effect.
Our choices, even small ones multiplied by millions of people, they can make a difference.
So it's not just about waiting for governments or big companies to do something. We all have a part to play.
Exactly. Every choice we make, the food we eat, how we get around, it all adds up. And it's not just individual actions. It's about working together, pushing for policies that put the planet first.
Okay, so individual actions, A&D, collective action. Got it. But with all these complex problems, where do we even start?
Well, chaos theory teaches us to think about systems, to see how everything's connected. We need to look beyond simple solutions and find those leverage points, the places where a small change can ripple through the whole system.
So instead of just focusing on, say, reducing emissions, we need to think about everything Biodiversity, forests, the oceans.
That's it. It's about addressing the root causes, not just the symptoms. And it means working together, scientists, economists, policymakers, artists, activists, everyone, to create a better vision for the future.
You know what? I'm starting to feel a little more hopeful. It's not about giving up and saying it's too late. It's about using our knowledge and creativity to face these challenges head on.
That's the spirit. And it starts with changing how we see things. The Gaia hypothesis, it asks us to see ourselves as part of nature, not separate from it. We're not just passengers on this spaceship Earth, we're part of the crew.
So instead of trying to control nature, we need to learn to live with it, realizing that our well-being depends on a healthy planet.
That's it. We're all part of something much bigger than ourselves, a web of life that supports us all.
Wow, this deep dive has been incredible. We started with basic physics and ended up talking about the fate of the planet. It's amazing how these ideas all connect.
We went from chaos to the possibility of order, from the Earth to space. It's been quite a journey.
And it's made me realize that we have this power to disrupt things, but also to heal, to create, to build a better future.
Yeah, it's a reminder that we all have a role to play in shaping the future, not just for ourselves, but for all life on Earth.
So as we wrap up our deep dive into deep simplicity, I want to leave you with this. The universe is this complex, beautiful, ever-changing thing, and we're all a part of it.
And the choices we make today, they'll shape what that universe looks like tomorrow.
Thanks for joining us on this amazing adventure. Keep asking questions, keep exploring, and keep diving deep.
And never lose that sense of wonder.